Hi, everyone, and welcome to Virtual Live at Frost Science. We're very excited for our presentation today. But before we begin and introduce today's special guest speaker, I want to take a moment to remind you that presentations and programs such as this one, part of our Virtual Live at Frost Science series, are made possible through the generous support of our viewers and museum guests. As a nonprofit, we rely on your generosity to advance our mission and serve our community. Here in South Florida and around the world, this week we are participating in Give Miami Day, and we need your help. Please visit givemiamiday.org/frostscience and make a tax-deductible donation to support Frost Science. Your support will help to keep us going, and please know that any amount makes a huge difference. The link is also included in the comments section. Now let's get into the fun part of today's presentation. I am Angela Colbert. I am the Knight Vice President of Education here at Frost Science, and I'm very excited for our topic today, which is Be True to Your Elements, an exploration into the periodic table. And it is my great pleasure to introduce our speaker, who is Chemical Kim. So Chemical Kim is a charismatic, motivational science education speaker advocating for science. Her focus in teaching science has always been to motivate students to investigate the world through experimentation. What a perfect speaker for today's Pride and STEM Day. And she's had so many wonderful local television station presentations, and she is a chemistry professor at Florida Southwestern State College. And her work definitely matters to the students all around her. And in 2011, she was the LGBTQ Pride co-chair in Kalamazoo, Michigan, and continues to work on improving LGBTQ visibility in STEM education. Chemical Kim, we're so excited to have you with us today. How are you?
Wonderful, and I'm really excited to be presenting the periodic table to you. How fun is this? This is a wonderful opportunity for you to learn. Yay!
Well, thank you so much. So the question I kind of always like to ask first is, what got you into chemistry?
You know, that's a great question. And it's interesting because I find this with a lot of people that go into science. It really starts at a young age. And I think many of us do have this when we're really young. And that's a curiosity. You know, you see things and you explore your world and you are wondering, what is that all about? Like, for example, even on something like, you know, the 4th of July, and you light a sparkler, or your parents light a sparkler, and you see that sparkling light. What is that? You know, when you see a flame color, why is it that particular color? When you see rust forming on a car, why is that rusting? You know, it was always those like, why questions that I had. And it really wasn't until I entered into my first chemistry class in high school that I started to get the answers. And it really just then made more questions, and it made it more exciting for me to find the answers to those questions. But chemistry, studying chemistry, gives me the tools to find those answers. Absolutely.
That's amazing. Well, I love chemistry. I was okay at it, but I love it. It's so fascinating. So I'm so excited for this presentation. So without further ado, please take it away.
Okay, I thought we could start off with, I'm going to share my screen on and off throughout this presentation. And what better way to get us started into the chemical elements but to sing a little song. Everyone, you're more than welcome.
Antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercurium, molybdenum and magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
So did everyone learn that wonderful song on the chemical elements? Because there'll be a test at the very end. You'll have to write and name every single one of them. I'm just kidding. I'm going to start the presentation off, though, just showing some of the elements on the periodic table. And I'm also going to talk about a time when within one particular nation in our world, the European nation primarily, that there was an interesting study of chemistry and the idea that the chemical elements, and you could take any of the chemical elements, something like copper, and I'm actually going to do this with copper, and turn it into another element, maybe something worth a little bit more, like silver, and how incredible that can be if it's even possible. But is it really possible? So we'll talk about that, and I'll show that. But the one thing I really want to also share with you in our understanding about these chemical elements, any material that you have in your world, anything that you find, as long as it has mass and it occupies space, we refer to that as having matter. That's actually matter. And the interesting thing, the most fascinating thing about matter is that if you break all matter down, it will be comprised of one or more of these 118 chemical elements in the entire universe. So chemistry is universal. I love that about chemistry. It doesn't discriminate where you're from or who you are. It really is reliant on what it's made up of. And it could be made up of, like I showed you, copper. It could be made up of maybe sodium if you're using a little bit of salt in your kitchen. So we'll be looking at some of these chemical elements. But what we know in science today that wasn't really known in some parts of the world in science, or many parts of the world, should I say, and that was that if you break down the chemical elements to its smallest size, you will actually see what are referred to as atoms. And so if you have, here's the fluorine atom right there. There's my chemistry lab here at Florida SouthWestern State College. And look, I can actually see atoms. But really what I'm actually showing, of course, is a virtual reality image of the atom of fluorine. Or if I wanted to maybe look at maybe an atom of phosphorus, a little bit heavier, a little bit larger atom. So every element on the periodic table, when you break it down to its smallest piece, so you basically cut it to its smallest piece, we would say that it is comprised of that atom, of that element. And each element has its own unique properties based on that atom. So what I really want to, though, definitely get in with you is showing you some of these elements and how I can use the knowledge of science to maybe manipulate some of these elements or, have a little bit of fun with them. And I'm going to start off with two of the lightest elements. And the first element, which is the lightest of all elements, is hydrogen. And in this balloon right here, I have hydrogen. Now, why do I have to put hydrogen in a balloon? Well, hydrogen's a gas, and in order to trap a gas, easily trapping it in a balloon. Now, what's unique about hydrogen is that I could get hydrogen from pulling apart a water molecule, right? Hydrogen, and this is a really crazy fact about the chemical element hydrogen, is that it's the most abundant in our universe. So abundant, it's abundant is 75%. Our universe, now I'm not talking about within the earth, our atmosphere, but within the universe, this is the most abundant element. But let me show you another really cool property about hydrogen. You might want to plug your ears if you don't like to hear the sound of a balloon popping, but I'm going to pop this balloon and I'm going to use a little bit of energy to do that, okay? Now remember, I mentioned that hydrogen, I could get hydrogen from water, okay? Well, what will happen if I combine hydrogen with oxygen? Because water is the elements hydrogen and oxygen. And if I'm going to add a little energy to this hydrogen balloon, I'm going to be combining it with oxygen. So think about this. If I separated water to make hydrogen, but then I recombine hydrogen with oxygen, will I make water again? Well, let's see. Okay. For safety, I'm using a lighted splint to add the energy. Okay, so a little flame. And again, you might want to pop your ears for this. I'll knock the lights down a little bit. Go ahead. You can, yeah, there you go. And 3, 2, 1. A lot of energy from that reaction of hydrogen in that balloon with oxygen. If that was a little bit too much for you, I'll do a little smaller one. Okay, so again, woo, the reaction with hydrogen and oxygen, and as much energy is released in that reaction, I really am just making water. And that's from the lightest element on the periodic table. You can see how much energy is released. Really fascinating. The second lightest element on the periodic table is helium. Again, a gas. And if you look in the universe, we're looking at 23% of our universe is comprised with helium. So hydrogen, again, 75%, helium 23%. Most of our universe is comprised of hydrogen and helium. So that doesn't leave much for all the other chemical elements, the 118 chemical elements that we study. Now, what's interesting about helium is it's what we call a noble gas. And noble gas is active, which basically means they're pretty introverted. They like to be by them. I'm going to do a little inhaling with this helium so that I'm going to pass my sound waves from my voice through a new gas. Instead of the atmospheric gases, I'm going to pass the sound waves through helium. And by the sound of my voice, if it works, you might be able to learn a little property about the heaviness of helium gas. Okay, so here we go.
So helium gas is a really, really light gas. And you can hear how it brings my voice high. Why does it bring my voice high? Well, because it's a light gas that my sound waves are passing through. Now, is that helium hurting my body in any way? It only would if I deprived it of too much oxygen, which I'm not, because I only took one breath. So it doesn't react with any of my body chemistry. It's really cool to see that behavior of helium gas with sound waves. Really, really cool. Okay, so what I'm going to look at next is, and I'm going to share my screen again, because I want to show you some of these next chemical elements that I'm going to be looking at. And that is on the periodic table. Okay. The first column on the periodic table, we are going to be looking at what are called the alkali metals. And the alkali metals are actual metals, but they actually are not very stable like we have in regards to the noble gases. Okay, so like I mentioned, the noble gases really don't like to react with anything. The alkali metals, and what I'm talking about are these elements: lithium, sodium, potassium, rubidium. And then cesium and francium, very low in abundance, especially the francium. But these metals are very reactive. You will not find these in nature in their pure form. And let me just show you, just as a simple demonstration. Actually, I'm going to do my second demonstration. Yeah, I'll come back to this one. So I'm going to show you a quick demonstration with the sodium in water, just to show you this reactivity. Very thankful to have my assistant, Kyra, who definitely has learned a lot of chemistry. So she definitely
is someone that can be very helpful with this demonstration. But what I'm going to show you, so what I have here is just a dish that I'm going to put some distilled water into. And sodium is actually a metal that we store, and I'll put this underneath it, that we store usually in like a kerosene or some kind of oil that doesn't allow it to react with other elements, okay? And therefore, I have it here in this jar, and I'll show you my sample of sodium. And I'm just going to do a really small sample because it is very reactive. It is extremely reactive, okay? And I'm going to show this to you. And it's a really, really small sample. It does have some oil on it. And I know it's a bit see, but what I cut open this little piece of sodium so that you can see it is a metal. And a property of metal, so it's an alkali, I mentioned, it's highly reactive. And a property of a metal is that it's going to be, you know, that luster, that shininess. Okay, so I'm going to just cut this open a little bit. And what's interesting about these alkali metals is that they're very, very soft. So I could actually cut this with a butter knife. It is so very soft in, you know, and my share screen so you can see my video a little bit better. Okay, so here we go. I'll go a little bit larger on the video, but you can see how shiny that sodium metal is. Okay, that sodium is highly reactive. It's not anything I can leave out in the atmosphere because it will react. And I'm just going to show you a really simple and very safe. I'm wearing my safety glasses and I'm wearing gloves. Okay, because if I didn't wear the gloves with the sodium, I have moisture on my fingers and the sodium would actually react with my moisture. And that could be, you know, very dangerous as well. So I'm going to add a little indicator called phenolphthalein to this reaction. And phenolphthalein starts off clear and colorless. It does actually, I should say, it does have a little cloudiness to it, but for the most part, it's a clear and colorless indicator. And when the sodium reacts with the water, we might see a color change. So here we go. I'm going to put it into the water and you can see that color change, that pink color change. Now, I stepped back a little bit because what's happening is the sodium is floating on top of the water. And that sodium is reacting with the water and it's making sodium hydroxide and hydrogen gas. So it floats on that gas. I try not to use too much because if I use too much sodium, it would actually explode. And as much as I love science, I definitely always try and keep myself safe. And I don't want any exploding sodium when I'm at such a close proximity. But it really is a unique behavior of sodium. Now we're going to go to the next column on the periodic table. And I'm going to show you that. And I'll try and remember to turn off my share screen when I do this demonstration. But the next...
Quick question, Chemical
Sure.
Kim, because this has been really cool so far. I love exploding balloons, things that change color. If you did that, so that was with sodium. If you did that with lithium, would that produce a different color or a different reaction? Or kind of how would that work?
That is an excellent question. So what's unique about the way the periodic table is structured, as you see, I'm sharing my screen. So we are talking about that first column, not including hydrogen, because hydrogen, as I showed you, is a gas, it's not a metal. Well, the reactivity of those elements increase as you go down the column. So the lithium would still react the same way, okay? It wouldn't be as reactive. It would still produce a hydroxide with the water, and I would still see that pink color. But I'll tell you, you drop, and I'm just going to go a little bit farther down to rubidium. Oh my goodness, you drop rubidium, watch, I wouldn't be anywhere near that reaction because it's like a hand grenade in a bathtub. It is incredibly reactive. Cesium has been utilized in demolition. The only concern with putting cesium in a process like demolition or doing any reactivity with cesium is it is a bit radioactive. So they have to be cautious with the utilization of that chemical element. But excellent question.
And then it's fascinating because you combine sodium With chlorine, you get salt, and you can put that in water just fine.
Isn't that? Yeah. 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 I think that's so fascinating because the unique things, like I said, all of our material, including salt, you break it down to its small species, it will be comprised of one or more of the chemical elements. Well, sodium wants to give up an electron in its reactivity, and chlorine, hey, I'll take that electron. So they react and they calm down. And so you have a very safe piece of salt. It's fantastic. It's a beautiful marriage between sodium and chlorine. Okay, so I'm going to continue here. Unless there's any more questions, don't hesitate to interrupt and, ask away. I love the questions. But what I'm going to do is show, I have to go back to my share screen because I didn't show you the next set of elements I'm going to show you on the periodic table. And the next set of elements, and I have one in particular that I'm going to use for demonstration, is the column next to the alkali metals, column 1. The next column with beryllium and magnesium, beautiful metals. Look at this. Calcium, strontium. Anyone know what this column on the periodic table is called? If you guessed the alkaline earth metals, you're absolutely correct. And the alkaline earth metals are reactive, and they do want to react with other elements, not as aggressively as the alkali metals, but they are very reactive. So I thought I would show you the difference in the reactivity between the sodium, which floated with the hydrogen gas, that it was releasing on the water, with some calcium in water. Okay, now calcium, I can safely share this with you. It's not soaking in any kerosene or oil to keep it reactive with the atmospheric gases. Okay, I do have to have concern because it will react with, I would need water to react, but this is a sample. Here, let me stop sharing so I can show this video again. Okay, so this is a sample of calcium, and calcium, like I mentioned, is, again, an alkaline earth metal. It is reactive, but it's not going to be as reactive as the sodium. So I just want to show you that reactivity, and why not do another phenolphthalein comparison with this particular sample. So I'm going to put a couple drops of this indicator, phenolphthalein, into what I have here is a test tube with water. Okay, and I think it'll be a little bit better way to show its reactivity, because the difference between calcium in water and sodium in water also is that sodium floated on the surface of the water, where you're going to see with the calcium, it doesn't necessarily float. So I'm going to put a small sample here, and what you're going to see is it reacts right away with the water. Okay, and it almost looks like it's making a pink Pepto-Bismol, which I'm going to talk about Pepto-Bismol in a second with some chemical elements. But you can see it's forming another gas. And this gas is actually the same gas that's formed with sodium reacting with water. This is also making a hydroxide. So this is calcium hydroxide. And that gas that it's forming is hydrogen gas. Okay. And eventually, once it started to get into the reaction with water, it kind of sunk down to the bottom until it was completely reacted. So beautiful reaction, but definitely evidence of showing that hydroxide that gets formed in that reactivity. Okay, so we're going to move to another alkaline earth metal, which, we're going to look at magnesium and bismuth. And I mentioned the Pepto-Bismol. Okay, let me just share screen here in a second. And show you the two elements that I'm going to be talking about. Okay, magnesium is this beautiful metal, again, an alkaline earth metal. And then bismuth, where's bismuth located on the periodic table? Well, bismuth is what we would consider a post-transition, or some people even call poor metals. I don't like to call any metals poor, because look at that, the wealth of that beautiful metal. This is actually bismuth metal. And I do have a sample of my bismuth crystal, but this is another picture of a bismuth crystal. But what's unique about showing these two metals is that if you have an upset stomach or you're not feeling very well, you can actually drink these metals. Now, I'm not saying in the pure form, you drink them as a compound in a solution, just like when you're taking table salt. So you're not eating sodium in the pure form, but when you have table salt, you are eating sodium, okay? And it's the same thing with this, and I just want to show you these two metals and what I'm talking about with regards to these beautiful, beautiful chemical elements. So upset stomach, have you seen this blue liquid? Okay, it's called milk of magnesia because of the element that's in it, and that's magnesium. Okay, so milk of magnesia, and also because it looks milk-like. Okay, and milk of magnesia, it's a little powdery here, but if I show you this particular sample, you can see it looks a lot like milk. Okay, it just looks like milk. And that partly is due to whether the compound that magnesium is with will dissolve or suspend in water, how it behaves with water. But you can drink this safely as long as you're not drinking too large of quantities, and it can help with an upset stomach. So this contains the element magnesium. I actually do have a sample of magnesium to show you as well. And that sample of magnesium is right here. And magnesium is a really light metal. It's really light. We can use it in car parts because it's so light. It's used in many applications. So it's a really useful metal that we can utilize, but you can see that shiny, shiny metal. Well, I'm going to do a quick little demonstration because another purpose of magnesium is during the 4th of July holidays, some sparklers, again, utilized by definitely adults that know what they're doing with these sparklers, because this generates a lot of energy when it does ignite, but some sparklers contain the magnesium. Now, the safer sparklers don't contain the magnesium, which I actually am more in favor too, because I'll show you why, okay? Again, being that I've studied chemistry and I've worked with chemistry, I'm not too afraid to work with this metal that I'm actually going to burn. And I'm going to let it burn and then show you the product that I'm making after I have it burn. But I'm just going to say this right now. The reason you have to be really cautious when you burn magnesium is because it burns at over 2,000 degrees. That is incredibly hot. So I'm going to move items out of my burn location, and I'm going to ignite the magnesium. Now, this is going to be a bright light, and if it wasn't virtual, I would always tell people don't look directly at the burning magnesium. Okay, but that is a piece of magnesium. Beautiful, beautiful in its burn, absolutely. But again, so dangerous with that high temperature burn. And look, you see this white powder that forms right there with the burned magnesium, okay? This will actually crumble more into the white powder. This is now, like it just did, this is now magnesium oxide. So the magnesium combined with the oxygen and made a compound known as magnesium oxide. Not too different than my hydrogen balloon exploding, reacting with oxygen to make water. So it really is cool science to see that you can burn metals and make an oxide, like, you know, the magnesium oxide. Now, I also mentioned that heavier, you have some more questions?
Yes, we actually had a question about Pepto-Bismol. So Florencia wanted to know why drinking Pepto-Bismol turns your tongue black.
Oh, I did not know that.
I didn't know it either.
So. You know, to be honest with you, both of these, I maybe in my lifetime drank once. So I don't get too often on the upset stomach. So I am going to, now you just made my curiosity go again. I'm always asking why, and I love that you have that question because I honestly don't know. I never knew that Pepto-Bismol turns your tongue black, and yet it's pink. It's a pink solution. But if you look at the ingredients, and if you are curious like I am, when I do shop anywhere and I'm coming across something that's new, I always like to look to see what elements are inside that material. You know, what is it that we are eating? And in this, we are eating this element bismuth. And the crazy thing about bismuth, the crazy thing, and I actually want to share screen on this one because I want to show you how crazy I think this fact is about bismuth. Okay, so bismuth is a heavy metal, very, very heavy. Okay, on the periodic table, it is right next door to lead. Now, let me ask you this. Would you drink a solution of lead? Absolutely not. That is not something that is safe to consume. And then that Marie Curie, a famous scientist from Poland, actually discovered, and it's called polonium. Now, this element is radioactive. So it's crazy that we have this bismuth that's sandwiched on the periodic table between these two elements that I would never put into my body. So interesting science fact on that one. Usually when we see, we see that relationship on the periodic table, like I showed with the alkali metals, but that tends to be more in the columns and the groups, not the next door neighbors. Okay, but this is my sample of bismuth right here. Okay, this little sample of bismuth, and it's by bismuth crystal. It's pretty brittle. And one property about bismuth is that it melts at negative 271 degrees Celsius. Okay, so it actually won't take much. I'm just going to demonstrate very quickly its low melting behavior. I can use my butane torch to get a little bit of bismuth, as you're seeing, and I'm hoping I can at least get you to see. I can try and get this a little bit closer. Okay, what I want you to see is how low melting, and I know 271 degrees, you're thinking, no, that is hot. That would burn me, absolutely. But a lot of metals take high temperatures to melt. And bismuth actually is a very low temperature melting metal in perspective, in comparison to other metals. And I'll show you a little bit later on an even lower melting point metal, okay, that I could actually melt in the palm of my hand. Crazy, it's crazy. So that's the bismuth. The next thing I'm going to show you, I'm going to move back. So I showed you magnesium and bismuth with the Pepto-Bismol and the milk of magnesia. Now I'm going to go middle between those two on the periodic table and show you aluminum. Okay, now I know many of you know aluminum, absolutely, right? You have aluminum at home and aluminum sheets. Some people will call it tin foil, okay? But let me share my screen here again and bring up a little fact about this aluminum, okay? So yes, we have aluminum at home. And I don't want to say it's inexpensive, but I'll tell you, pre-1920s, it definitely is a lot cheaper than it was before the 1920s. Our aluminum, right here, sandwiched on the right side of the periodic table, right next to the metalloids, okay? At one time, before the 1920s, aluminum was actually more expensive than gold. Isn't that crazy to think that, like, this is more expensive than gold? A piece of aluminum? Seriously? But it is. It actually was. Now it's not. Now definitely gold is more expensive than aluminum. But the question is why? And the reason I ask why is because if you can see on the screen that I'm sharing, the abundance of aluminum in the Earth's crust. So the abundance of aluminum in the Earth's crust is 8.1% abundant. That is a very abundant metal that we have in the Earth's crust. That's highly abundant in comparison to gold. Oh my gosh, 0.0000000. Say all those zeros. 31% abundant, very low abundance. So why would something that is so low in abundance be more, something more in abundance, if I'm gonna say this right. So why would aluminum be more expensive than gold? Well, it happens that that when you look for gold in the environment, you can usually find it in its pure state. And the aluminum, no, we usually find it in a compound. And so it took a chemist, actually two chemists that kind of did it simultaneously, to come up with a process to separate the compound that we find aluminum bonded to in our environment and get it in its pure form. And when those chemists came up with a process that was a cheap process to do, it brought down the price of aluminum. So we start using aluminum for lots and lots of things. And one particular process is to make the Japanese yen coin. Let me stop sharing again. I always forget to stop share. I just want to make sure you can see this. So this is a Japanese 1 yen coin, and it's 100% aluminum. Okay. Well, I say it is 100% aluminum, but my sample has been sitting around for a bit, so it is a bit oxide. So it has aluminum oxide because it hasn't reacted with the oxygen in the atmosphere. So it's a little dirty, kind of, it's not pure aluminum. But what I do want to show to you, and I might just get this reaction started because it will take a bit for it to continue, is how, again, there was a time, and I'm going to, start with this reaction and then show you another one with the copper and the silver. How at one time in the European nation over 2,000 years ago, there was this belief that you could take a pure element like aluminum, a pure metal, and turn it into a totally different metal. And this stayed for a long time. This idea that you could do what's called transmutation was because instead of saying that an element is comprised of atoms, so the atoms of aluminum, there was a belief that the elements are comprised of 4 elements: earth, fire, air, and water. And those are known as the 4 Aristotle elements. So if you could just change the percents of those Aristotle elements, you could turn one metal into a new metal, do this magic transmutation, I guess, or the science of transmutation. Well, why did that belief stay for so long? Well, I'm going to show you why. At least one reason, I think. Okay. And what I'm doing is I'm adding this like bluish solution to my aluminum. I put my little aluminum Japanese 1 yen onto this paper towel. Okay. And I'm just dripping this blue solution. Now, keep in mind, back in the day that this was a belief that I could turn one metal into another, where would I find this blue solution? Well, maybe I was hiking in the mountains one day and I came across a mineral and I chopped up that mineral, I crushed it up, brought it back to my lab and dissolved it in acid, or maybe tried to dissolve it in water. And then, hey, why not throw a piece of aluminum into this blue solution? And I did. And what's really fascinating is that what I see forming, and I'll let it sit a little bit longer, so if at the end I can show you more at the end, but what I see forming is actually copper. So copper is forming on my Japanese yen. Well, of course, now that we understand atoms, and I think many of you that are watching can understand that the copper is actually this blue solution. So it's not like I did transmutation, okay? The copper is here. But back in the day that there wasn't that full understanding of science, and we're always learning, we're always advancing what our knowledge and questioning. And you can even question me. Maybe I'm not right, to prove that I'm wrong. That's what I love about science. So that is the copper that is forming right there. So let's go from this to taking copper and making silver, okay? And this behavior is really unique because silver is worth more than copper. And as I showed you with the Japanese yen penny, or not penny, but it's the Japanese yen, and the American penny we know is made out of copper. Now, the concentration of copper, the amount of copper that we use to make the American penny, of course, has changed. But it's an interesting fact that a copper penny is actually worth more than 1 penny. Even the newer copper pennies, I think it takes about 6 cents to make a copper penny. So that's an interesting fact. So this is copper, which is a pure element. If I break it down, I'll have its unique atoms of copper. And this is silver, which again is a pure metal element. And if I break this down, it'll have atoms of silver. The atoms of this copper are going to be different than the atoms of this silver. But if I show you this little demonstration, again, to go back to that belief that maybe I'm wrong and maybe the copper is not comprised of its own atoms, but copper is actually comprised of these 4 elements, the air, fire, earth, water, the Aristotle elements, right? And what if I change the percentage of those elements in copper to get it to match the percentage of the elements in silver? So as an alchemist, again, taking a hike in the mountains, I come across some rocks. I bring them back to my lab. I crush those rocks up in the lab and I dissolve them in a little bit of nitric acid. And then I see, well, what if I add that solution that I filter out from my rocks and the nitric acid? What if I add that to the copper? Okay. And it looks like water, the solution, which is really crazy. Now, I think this is a really good lesson because not all materials that look like water are water. Many of them are not. So always be safe whenever you're looking at new material and you're not sure what it is. Just because it looks like water doesn't mean it is water. Oh my gosh. What am I seeing? I'm seeing a formation. Something is forming on my copper. Wow. Now, because of the time, and I do want to share a bit more science with you, I actually started this demonstration before my presentation, and I let it sit even longer. And you can see in this test tube is a beautiful sample of silver that has formed on my copper. Now, did I do transmutation? Did I take one chemical element, copper, and turn it into another chemical element, silver? Now think about it. From what I explained with the yen penny and the copper chloride solution, could there be a similarity in this reaction? So it's fascinating, and it's really, I think, gives us a good lesson into the past at how chemistry used to be viewed. So that's really unique. It's also, you know, I kind of feel like this alchemist whenever I do that. So quick question.
So that's actually silver that you made on the copper?
Silver. Oh my gosh, that's crazy. That is silver.
Really?
Nope. In fact, because I get all geeked out about my science, I did this, you know, a couple of days ago, and I filtered it out. And I know it's not always good to see on camera, but I do have my silver residue right here. This is silver, little specks of silver. Yeah. I mean, there's still some little pieces of copper. Oh, and think about it, is that my copper, my original piece of copper actually did get lighter. My solid copper, keep that in mind. Yeah.
That is so cool.
Yeah, it's like transmutation. It's almost like, you know, you really do feel almost magical when you do this chemistry. There's no question. So the next that I want to move into is the middle section on the periodic table, which are known as the transition metals. And there are some of these metals that you have experienced and maybe encountered, or many of them, I should say, but there might be some new ones. But one in particular, this element, and it is known as iron, right? I think this is the one that many people are probably, between this and copper. Oh, copper is a transition element, and same thing with silver as well. But because you can see it's in that middle section on the periodic table. Okay, so I guess I'm not moving into the transition metals, I'm continuing in the transition metals. But copper, but iron, like you see with this particular sample of a horseshoe, okay, whenever I ask, you know, when I'm teaching and I'm asking students or I'm talking to kids, you know, I always ask, can I burn a horseshoe? You know, could I take my flame right here, okay, and actually take the butane torch and actually burn a metal horseshoe? Well, no, but you can burn iron. And I don't think too many people are aware of this. I mentioned the 4th of July sparklers. Well, 4th of July sparklers have been put into a different composition since, like I mentioned, the magnesium. And many of the 4th of July sparklers contain iron, okay? And this is a sample of iron that I can burn. And the reason that this is going to be easy for me to burn is because I'm giving it more exposure to oxygen, okay? And it, as we know, it will sit and react eventually, and it will turn to rust that we all know as iron oxide or iron 3 oxide. But I can simply burn, and I'll show you even so much so that I always kind of consider this wizardy science. Okay, I'm a big Harry Potter fan, for those of you that do like the Harry Potter story. And I always, whenever I do this particular demonstration, I like to say the spell that is said in Harry Potter when it comes to making light. And if you know the spell, you can say it with me. So you ready? We're going to say lumos. Ready? 1, 2, 3. Lumos. And I just made light. I am actually changing iron from its pure form into an iron oxide. And I didn't even turn on my butane torch to do that. So that's pretty science. Now, I needed oxygen to do that, right? Oxygen is an incredibly important element, not just for the sake of life, but also when it comes to our chemical reactions, we need oxygen to burn. And in our atmosphere, we actually don't have a lot of oxygen in our atmosphere as much as you think we do. There's plenty more nitrogen than oxygen in our atmosphere. So I'm going to make a little bit more oxygen, okay, than I have in my atmosphere. So I'm going to combine two liquids to make a bit more oxygen. And when I do this, I hope you'll see a difference in the burn, having more oxygen available for the burning of my iron. So I'm going to do that, and I might even have the lights knocked down a little bit to maybe make this even more visually appealing, and it's wizardry kind of science. Okay, so I'm going to make my oxygen, and what you're going to see when I show you this demonstration, when I pour this next liquid into this beaker, you're going to see a gas, and that gas actually is a very safe gas because it's the oxygen. Okay, it's that oxygen that I need. Now, when I say safe, it's safe because of the fact that it's going into the atmospheric gases and mixing with the other oxygen that's also present. But of course, I wouldn't want oxygen 100% because that is an oxidizer, right? So here's my bubbling gas that's produced. There's my oxygen, and don't look away, don't look away. And there's the strong burn, that strong reaction with oxygen in burning iron. So I hope you saw a big difference between that burn and then just burning it in the presence of just the atmospheric oxygen. And also what's really interesting is this is a container that I use this demonstration for. And down at the bottom, I do see the iron oxide, but I also see little beads of iron. So that reaction produced so much energy that it did melt, not only oxidize, but it did melt pieces of my iron. Okay, I'm going to move to my next favorite element. I know I'm getting to the end, so I'm leaving my two favorite elements to show you to the last. And this one is absolutely my most favorite, so much so that I'm going to come in contact with it. And I'm going to do gallium. Okay, I'm going to show you gallium. And gallium, being that it's my favorite element, so I grew up at a time that we had a lot of mercury thermometers, and mercury thermometers are not exactly safe thermometers if they break because of that exposure to mercury. But I was a kid that, and maybe it was because my educators didn't know so much about this. I was a kid, I might not be able to show this one to you because I need to heat this up a little bit to get it out of the container. I usually have a little chunk that I can fall out into my hand, but don't worry, it only takes about 5 minutes to warm this up. But inside this container is gallium, and I'm going to show you liquid gallium that looks just like liquid mercury. And as a kid, I used to, not too often, thankfully, but I used to actually touch liquid mercury. It's not safe to do, but again, we didn't really know so much of the facts that we know today about it. So I can now safely touch gallium, though. Gallium's a very, very safe element. So I'm going to go put this on the hot plate just to warm it up a little bit more to where I can get a sample out and show you. But while this is warming up, I'm going to go back and show you iron again, but in a different state. Okay, well, I don't want to say different state, but kind of in a different form. I'll just leave it at that. So let me just go put this on the hot plate. Take it off, yeah. Okay, so what I have here of course, is just a bolt, okay? And inside this container is something called ferrofluid. This is really, really unique material. It's actually little micro or nano-sized particles of iron. So little, it's the same iron that you would find like in black beach sand, okay? And it's suspended in a carrier fluid. And that carrier fluid could be anything from water to citric acid to an organic solvent, okay? And it creates this material that we call ferrofluid, but it mostly is the iron and the iron behavior that you're gonna see when I put this ferrofluid onto the bolt. And I'm not gonna reveal 100% how I set up this experiment, okay? I'm gonna lift it up a little bit just so you can see. I'll put a little bit more. And for those of you that follow me on social media, on my TikTok, this was one of my most popular TikTok videos that I shared. So if I do have any of my TikTok followers that have been curious about this particular material, yes, it is safe to touch. Like I said, it's just iron. It's just like the iron that you find in the sand. And if the carrier fluid is just water, okay, it is completely safe. And it really looks like it's like stuck to that. Now, I didn't reveal the secret, and this has to do with the property of iron. I have a magnet, a really strong magnet at the bottom. So I magnetize this bolt, okay? And what's really cool to see is how iron, which is magnetic, and these really small nano-sized particles in the carrier fluid, how it will position itself in these peaks to minimize its energy. It is a really, really unique behavior of iron in a carrier fluid. And of course, I'm working with a magnet. So I'll just kind of like, that might be even a kind of a cooler way to see how it just stays. You think I could tip it over without it spilling? Let's see. There it is. Okay. Really, really cool ferrofluid. So that's iron. Okay. So I have two last to show you. And while my gallium heats up, I'll do my very last, or the second to last, and then I'll do my gallium. So right now I'm going to just share my screen. Well, actually, you know what? I'm not going to share my screen, because if I share my screen, you're going to see the actual element that I want you to see for the first time here live virtually. Okay. And this is liquid nitrogen. So if you want to bring over the white, just bring the white container to me, and then I'll have you hand everything over. Here we go. Okay. So I have inside the speaker, or not inside the speaker, inside the styrofoam container. Okay. I have this, and I actually don't use, I know many of you will think it's incredibly cold, but I don't use gloves when I work with this liquid, even though it's negative, like near negative 200 degrees. It's not because I don't want to be safe, but I find that when I spill this on my gloves, it will actually freeze my hand. So I feel safer not to wear gloves to show this to you. This right here is liquid nitrogen. Okay, and liquid nitrogen, like I said, it's negative 195.8 degrees Celsius, negative. So what it's doing right now is it's boiling, okay, and it looks like water. It just looks like water. But let me show you, I'll bring it back to my spot right here with the balloon, how cold this is, because as we know, this balloon just contains atmospheric gases. I just blew it up, and it has oxygen and nitrogen, okay? And I might even move this back a little bit more. But what I'm hoping you're going to see with putting a balloon inside liquid nitrogen, I'll even put both ends here. There you go. See that? Look at that. Look at how it's condensing the gas inside the balloon. The liquid nitrogen is cold enough that it will condense the gas. It's crazy cold. Okay. Let me show you with some flowers. Oh, wait. And then it expands. Oh, look at that. It's like magic. It's magic, right? I condense the gas, and the gas warms up and expands in the balloon. Let me show you the coldness now of liquid nitrogen by taking flowers, which, as you can see, are very soft petals and comprised a lot of water. Okay, if I put this into the liquid nitrogen, and Ooh, look at that. Look at that water vapor. That's not smoke, right? That's water vapor because of the vapor of the water in our atmosphere. Okay, but I'm getting these flowers really cold, and watch when I crumble them with my hand. Ready? I use the strength of science to crush a whole bunch of flowers. But really, flowers are comprised mostly of water. So all I did was just freeze the flowers and crush them. So liquid nitrogen is so incredibly cold. The last thing I want to show you with the liquid nitrogen, because I know I'm getting to the end here, and for those of you that have only set up for this time, I want to show you quickly, before I do the gallium, how liquid nitrogen behaves with water, okay? And it's kind of a battle that I make with the liquid nitrogen and the water. You probably take the gallium off, right? Okay. So here I have water that is warm enough to touch. Liquid nitrogen, as I mentioned, negative 195.8 degrees Celsius. When you add water to it, it's almost like there's a battle that's taking place. But it is providing more energy, more heat energy to the liquid nitrogen, allowing nitrogen to do what it wants to do, and that is go into the atmosphere as a gas. Because we do have our atmosphere filled with liquid nitrogen. So if I use enough water, I can get this liquid nitrogen to boil even quicker. But it's kind of a cool thing to see that water vapor that gets created. Okay, so I'm here at the end. Let me see if I can get a little sample of gallium, save my favorite element for the end. Absolutely. Okay, so, oh yes, you are in for a treat. At least I feel, because this is, again, my favorite element. So gallium, like I said, melts at a very low temperature. I could melt it in my hand, but just for the sake of being able to do this demonstration, I melted it on a hot plate, okay? And I'm really just trying to show you quickly. It looks like I just poured mercury on my hand. It looks like I just poured mercury on my hand, but I didn't. It's gallium. And gallium, look at that. It is a metal. Some people say it looks like the Terminator metal, maybe, but it was a later discovered element, and it's very safe in comparison to mercury. It is very safe to be touching this gallium. And you notice it leaves like this tinge on my hand, like I'm playing with graphite, like a pencil, a leaded pencil. So that is to end my presentation with my favorite element, gallium. And hopefully you enjoyed and learned a little bit about the periodic table and the chemical elements. So thank you all for joining. If you have any last questions, if there's time, I'm more than happy to stick around and answer any questions.
Thank you so much. That was amazing. We're like over here taking notes because it was so cool.
And I'm just going to be playing with my gallium.
Yeah. No, that is awesome. We love learning about all these kinds of elements, and gallium. It really does look like the Terminator. That's the first thing I thought of.
Yeah, crazy.
That is so cool. But so they were asking from the beginning, where can they find that periodic table song?
Oh, okay. So what the mobile app that I shared with you, it should be on most, I think it is on every device now. But of course I'm actually screen playing from an iOS and iPad, but it's by Theodore Gray. And here I'll share screen really quickly just so you can see the author of this app. Okay. And he actually included, so there, Theodore Gray, the chemical elements. He packages a couple mobile apps, which are fantastic. And he also does show a lot of chemistry on his mobile apps, but he also has the song. If you noticed when I played that song, he has a Japanese version. So kind of cool. So you can definitely have a lot of fun learning chemistry. That's a wonderful mobile app because the periodic table is visual, and it's my favorite visual periodic table app. Yeah.
Absolutely. So the last question is the one that I had for you that I was saving for the very end. Today we are celebrating Pride and STEM Day. So I wanted to know if you had anything you would like to say to any scientist of any kind out there that are looking to maybe get into science, but especially those who are LGBTQ plus. Thank you.
Yeah, no, I appreciate that you are allowing me to share during this time. So, as you know, I love science from a young age, and I think the one thing that science always made me feel safe about was that it was universal. It's regardless of who you are, what you look like, how you feel, who you're attracted to. Science never gave me a barrier. And I will, share on a personal side, I went through high school in the late 80s. And as crazy as this is, I identify as a gay woman. Pronouns are she, her. And so during the time of my adolescence through high school, I actually did not know any gay women, whether it was, teachers or even friends or even other people in my school, even all the way through college. And so for my identity, it took almost 15 years after my education to really have a good understanding and acceptance. And I think that's more of the word acceptance of who I am. And so I think that with regards to being who you are, and you're ever feeling like I'm trying to fit in with a specific group of people, or, I'm trying to fit in with my family in terms of how, my family has expectations of me. Absolutely, families are number one, but they want you to be you. Your family wants you to be happy. Your friends want you to be happy. And when I truly identified and was allowed to identify and come out publicly as a gay woman, I was very fearful, I'll be honest with you. But the one thing that I see now that offered the beautiful transition that I went through was that my family saw me happy and they saw me genuine. And they actually, I think, found me to be even more enjoyable to be around because they had a happy mom, they had a happy friend, they had a happy sister, they had a happy daughter. And not really coming to grips to my identity made that really difficult in my young years, So I'm always here. I'm Chemical Kim, and I always love to connect with anyone that, feels lost or feels confused, or even is a bit geeked out about science and education. And, definitely reach out to me, kim@chemicalkim.com. And I'm a safe space, and hopefully you can find also in your community some safe space and teachers and other counselors and even, Frost Science that they offer this program. They're a safe space as well to be who you are, embrace science, embrace yourself. That's what I would say.
That is beautiful. Thank you so much for sharing that. I'm sure that's going to really resonate with a lot of our viewers. So thank you. And yeah, we want our scientists to be as unique as all the elements of the periodic table.
Yeah.
So,
one last thing. You're wondering also about the hair, science. So if you want awesome hair, science.
Perfect. I love the hair, to be honest. I could never pull that off. So I am very much in awe of you for many, many reasons. Thank you so much again for joining us.
Thank you.
It's truly been a pleasure. So as a reminder for everyone who was watching, today, if you enjoyed this presentation, it is Give Miami Day tomorrow. You can start giving even today if you want. They opened it up early this year. So it's our largest philanthropic giving day here in Miami. So givemiamiday.org/frostscience will continue to support programs like this that hopefully continue to inspire scientists of all ages and science enthusiasts of all kinds. So thank you so much, Chemical Kim, again for joining us, and have a wonderful Thanksgiving week next week.
Yes, everyone stay safe. Everyone stay safe, and If you get bored at Thanksgiving, you can always do science in your kitchen.
There you go. It's very true. Thank you again, everyone, and have a wonderful day.